Okay, let's dive into this. Welcome to the Explainer. Today, we are cracking open the genuinely fascinating world of programming. And, at its absolute core, programming isn't magic. I know it can look like it sometimes, but it's really just the process of giving a computer a highly specific, organized set of instructions. But the real puzzle is, how exactly do we do that? Because it all boils down to this one fundamental question, right? How do we take our fluid, messy, incredibly complex human reasoning and translate it into strict, concrete machine action? Well, today, we're going to act as your guide, and we're bridging that gap step by step. We'll explore the vocabulary, the grammar, and the structures that make up the language of computers. Let's move to and see how this builds. Here's our roadmap for today. We'll start with the fundamentals, variables and constants, then move into sequence, selection, and iteration. After that, we'll explore operators and string handling, look at procedures, functions, and libraries, and finally wrap up with arrays and file handling. Sound good? Let's get started.
Section 1. Fundamentals, Variables, and Constants.
Okay, so before a program can actually do anything, it needs to hold on to information. Think of a variable as a dynamic storage box right inside the computer's memory. As a programmer, you give this box a specific name, and whatever you put inside it can and likely will change while the program is actually running. For example, imagine you're playing a video game. Your high score is constantly updating, right? That score is stored in a variable, dynamically reacting to your inputs and the game's activities in real time. Now, in complete contrast to that, we have the constant, and it is exactly what it sounds like. Once you define a constant, you are locking that value in place. It will stay exactly the same every single time the program runs. So if you've got a game that always gives players exactly 60 seconds to finish a level, that 60, that's a constant. Or if you're writing a program to calculate the area of a circle, the value of pi, 3.14, is a constant that literally never fluctuates. Now, when we talk about numbers in programming, we have to be pretty specific. Enter the floating point. Basically, this is a number that contains a decimal point. We call it floating because the decimal point can, float around depending on the number. This helps the computer efficiently handle incredibly large or, on the flip side, very precise fractional numbers. You'll also hear this referred to by programmers as a real number. Now, what's really interesting about this slide is how practically all the basic data a programmer uses fits neatly into one of these 5 primary categories. You have your integers, which are just whole numbers, positive or negative, like 34. Your reals, or floating points, like 34.19. Then there's char, short for character, which is just a single letter, number, or symbol, maybe a pound sign. String is a combination of characters mashed together, like the entire word program. And finally, Boolean. This is strict binary logic. It only ever returns a true or a false value. Section 2, sequence, selection, and iteration. So now that we have the vocabulary down with our data types, we need to learn the grammar of our code. How do we actually structure these instructions so a computer understands them? Well, the first fundamental construct is sequencing. Instructions absolutely must be carried out one after another in a strictly determined order. Just look at this everyday algorithm for making a cup of tea. It makes perfect sense to us, right? But computers do exactly what they are told, mindlessly. Imagine if step 5 happened before step 3. The computer would literally just sit there furiously stirring a dry tea bag in an empty mug. Getting the sequence right is absolutely critical. But obviously, programs can't just be a single straight line. They need to adapt. They need to make decisions. And this is called selection. An IF statement allows a program to ask a question and branch off. Think of a GPS app. If the user is driving, then show a roadmap, else show public transport routes. It's incredibly powerful. Now, for scenarios where you have a bunch of different, very specific outcomes, we use case statements. For example, you could program a case statement to output a different day of the week depending on the type of clothing a user inputs. Type in shirt, it outputs Monday. Type jacket, it gives you Tuesday. And the final piece of our grammatical puzzle is iteration, which is just a fancy word for looping. Instead of typing the same exact instruction 20 times, we just tell the computer to repeat it. There are 2 main ways to pull this off. A for loop is count controlled. You tell it exactly how many times to repeat, like, say, adding 3 lives to a player's score. A while loop is totally different. It's a precondition loop. It repeats endlessly as long as a certain condition remains true. Think of a smart home program checking if your front door is shut. It'll loop asking, is the door shut? Is the door shut? Over and over. And it will only end that loop when you finally confirm that yes, the door is closed. Moving right along to Section 3, Operators and String Handling. All right, so we've got our data and we've got our loops. Let's look at the punctuation of our code, how we actually calculate and manipulate the data we've safely stored away. Remember our string data type from earlier? Programmers can manipulate text strings in some brilliant ways to personalize user experiences. You can use length to find out exactly how many characters are in a user's password. You can use position to pull out, say, just the third letter of their name. You can use substring to extract a specific chunk of text, like pulling the re out of the name Greg. Or if you want everything looking clean and uniform, the upper and lower methods easily convert text cases. That guarantees that no matter how messy or weirdly the user types their name, it formats perfectly on the screen. Section 4, Procedures, Functions, and Libraries. Now, as programs get massive, and I mean millions of lines of code massive, writing the same logic over and over becomes incredibly inefficient. Programmers need a way to group code into reusable paragraphs. When you group code into a function, let's say a function that constantly calculates a game character's health, you really have to think about where your variables live. We call this variable scope. A local variable is declared inside that specific function and can only be used right there. It's safe, it's isolated. A global variable, on the other hand, is declared outside and can be accessed and modified by literally any part of the entire program. Managing those securely, that is the hallmark of truly great coding. But here's a secret. Writing efficient code isn't just for the machines. It is a highly collaborative process for humans, too. You could write the most brilliant, mind-bending algorithm in the world, but if you name your variables item 1 and item 2, the next programmer to look at your code is going to be completely lost. Maintainable code requires meaningful identifiers, and it also requires clear commentary. These are little notes written right alongside the code that the computer totally ignores, but humans read to understand exactly what that block of logic was actually meant to achieve. And finally, Section 5, Arrays and File Handling. So, the crucial point is, we are now going to look at the programmer's ultimate filing cabinet. This is vital for managing massive amounts of data efficiently. Imagine you need to store 5 distinct colors for a program. I mean, sure, you could create color_0, color_1, color_2, and so on, but that wastes time and completely clutters up your memory. So how do we solve this organizational problem elegantly? The answer is an array. Think of an array as a series of memory locations all grouped together under one single name, storing the exact same data type. Right here, we have a simple one-dimensional array containing 5 colors. To pull out the word blue, you don't need a new variable. You just ask the program to look at index number 2. And actually, yes, if you're looking closely, you notice that right. A fun, slightly weird quirk of computer science is that computer counting almost always starts at 0, not 1. So an array holding 5 items is indexed from 0 to 4. To wrap things up, we have file handling. Think about it. A program might take weeks of user data input. But if all those variables and arrays just exist in the program's live active memory, the moment you close the application, all that data vanishes. Just poof, gone. File handling allows a program to open an external file, like a simple text file, permanently write that data to it line by line, save it, and properly close it. That way, the next time you launch the program, it can read that external file and pick up exactly where you left off. And this brilliantly illustrates our entire journey today. This mind map summarizes the incredible interconnected ecosystem of programming. From deciding between a constant and a variable, choosing the correct data type, building logic with sequence and selection loops, organizing it all elegantly into functions, and finally filing it away securely in arrays and permanent external files. Which leaves us right back where we started. But now, you're armed with the tools of the trade. You have the vocabulary, you understand the grammar, and you've got the filing system down. The machine is waiting. So, now that you understand these foundational building blocks of code, what complex human logic will you translate into machine action next? Thanks so much for watching this explainer, and hey, happy coding.